All right, so today we're looking at geometric proofs. Now I could do hundreds of examples of geometric proofs, but I'm just going to do one. So in this particular case, it says prove the diagonals of a rhombus are perpendicular. So first of all, we need to draw ourselves our rhombus. And here's our rhombus. And we need to know some things about a rhombus. And in particular, things that we know about a rhombus is that opposite sides there are parallel. All right, so those two sides are parallel, these two sides are parallel. Now, not only are the sides parallel, the opposite sides are the same length as well. So I need to somehow, I'm going to work off this point there, and so that's point O. Here's point A, point B, and point C. So we know it's a rhombus. So what do we know about a rhombus is that these two sides here, OA and OB, and not OB, OA and CB, they're parallel. So in terms of a vector, they're in the same direction. But not only are they parallel, but they're also the same length. So this vector and this vector are then essentially the same. So we're not talking about position vectors here, we're just talking about vectors. So same length pointing in the same direction. And then of course for these two sides we've got the same thing. So OC, not only is it the same length, but it also points in the same direction as AB. All right. Now, the other thing we know about a rhombus is that a rhombus is a square that's been pushed over. So what we then know is we know that the lengths of OA and the lengths of OC are the same. All right, so that's what we know. So all of that so far is what we know because this thing's a rhombus. All right, now where we're going from here, we're going to use some different things from here now. All right, so when what are we asked? We're asked to prove the rhombus, the diagonals are perpendicular. Okay, so here's our diagonals. There. So our diagonals are AC and OB. All right, so diagonals are AC and OB. So now what we need to do, and it's saying here, prove that they're perpendicular. Now what we know about perpendicular vectors, hopefully, so if perpendicular, then AC, the dot product with OB, must be equal to 0. So remember, because that's the magnitude cos of the theta. And if they're 90 degrees, theta's 90, cos of 90 is 0. So AC.OB is 0. All right, so they're the things that we know. So there's a whole heap of stuff that we've got out of this. All right, so you've got to break it down, try not to do too much all at once. So start with your figure. Figure's the rhombus. What do we know about a rhombus? We know these sides are parallel. We know these sides are parallel. We know the lengths of all the sides are the same. That's what we know. What does it want us to know, prove about? It wants to prove about the diagonals. There they are. What does it want us to prove about them? They're perpendicular. So what do we know about? What have we got that we can work out? Like we're talking about vectors. What have we got? Perpendicular is an angle. So what have we got with the angle? That's the dot product. All right. Now we actually start doing some calculations. So what is OB? So OB, from there to there, that's OA plus AB. All right. Now, AB of course, is the same as OC. So that's OA plus OC. All right, so there we are there with that. The other diagonal is diagonal AC. So how can we go from A to C? We can go A to O, O to C. We can go A to O, plus O to C. All right, which of course is A to O is the opposite of O to A, plus O to C. So OC minus OA. All right, that's where we go. All right, so far, that's what we've got. So now we're looking at the dot product. So the dot product of AC and dot product with OB. So in terms of what we got, that's the dot product of OC minus OA with OA plus OC. All right, so now we need to expand some things out here, do the dot product. So that means we've got the dot product of OC and OA. Then this dot product between these two. So the dot product of OC with OC. Then we've got this one minus the dot product of OA with itself. And then minus the dot product of OA. Yep, OA with OC. Now, when we look at this, you'll notice you've got an OC.OA and an OA.OC, or otherwise, excuse me. So they're the same, but we've got a minus here. So we've got once there and we're taking it away there. So what are we left with? We're left with OC, dot product with OC, minus OA, dot product with OA. Now, remember, of course, back to our this bit here, because of the angle between. So if you like OC.OC, is the magnitude of OC times itself. Cos of 0, and cos of 0 is equal to 1 minus the magnitude of OA squared, and again cos of 0, which is 1. So we've got the magnitude of OC squared minus the magnitude of OA squared, and because it's a rhombus, and we know that the magnitude of OA and the magnitude of OC, this length and this length, they're the same. So effectively we have here the magnitude of OC squared minus the magnitude of OC squared, which of course then, this is going to jump, note it probably, this is going to jump, no, equals 0. And so if that equals 0, we know when a dot product is equal to 0 that the angle is 90 degrees. So the angles, diagonals of a rhombus are perpendicular. So they're at 90 degrees to each other. Alrighty, so there's that example there. So you've got to work through these proofs step by step. Don't get ahead of yourself too much with it. And as I pointed out up here, from not very many words, there's a lot of information. All right, so break it down, very, 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 very specific on what you're breaking it down to before you jump into actually doing the calculations. Write all the stuff you know. Write all the stuff you know. What you know, then get into it after that. All right, if you need any assistance, of course, make sure you get some, and as always, have fun.